responding to the topic of the meeting, I wanted to talk about, and since I'm interested in gravitational waves, I wanted to talk about one of the really major moments in the advent of multi-messenger astronomy, which is the detection by LIGO and Virgo of the first binary neutron star merger only a couple of years ago now. So I wanted to begin, though, and I'll be just sketching things in, drawing on the work of other people rather than my own original work. A little bit on the background of this, because of course there's quite a long genesis. How did we get to the stage where we even imagined that things like neutron star binaries existed, not to mind detecting them? And probably a lot of people here at this workshop will be familiar with the origins of the ideas of neutron stars. I'm going to sketch it very, very briefly given the time constraints. Of course, I think most of us are familiar with Chandrasekhar's work on the mass limit of white dwarfs, which showed that electron degeneracy pressure, which was, of course, already when Chandrasekhar was working in the 20s and 30s, a very new idea, was realized by Chandra and actually others independently, including Lev Landau, whose picture you see here, that there was a limit to the mass that electron degeneracy pressure could support, and therefore there was an upper limit to the mass of white dwarfs. And there was an obvious question, well, what happens if you have a star that has a core more massive than that? And the answer, of course, is that you have then a neutron star. And I think most people who are interested in the history of astronomy and astrophysics know that Lev Landau and Fritz Zwicky and Walter Baade were amongst people who anticipated who introduced the idea of the neutron star back in the 1930s. There's a very nice paper, the title Lev Landau and the Conception of Neutron Stars, the authors Dmitry Yakovlev, Pavel Hansel, Gordon Byam, Christopher Pethick, which actually looks a little bit at some of the details of how this idea arose. Niels Bohr's collaborator, Ralph Rosenberg, has a famous anecdote in which he recalls receiving the news of the discovery of the neutron, and Landau happened to be in Copenhagen, according to this anecdote, and again, in the impression given by Rosenberg, rather improvised the notion of neutron stars based on the discovery of the neutron in a discussion with Bohr and Rosenberg in Copenhagen. But this paper shows very convincingly that Rosenberg's memory was, as memories will do, playing tricks on him. He was conflating Landau's interest in neutron stars with Chadwick's discovery of the neutron and the fact that Chadwick wrote to Bohr telling him about it. There's strong evidence that clear evidence that Landau had actually written on what became neutron stars before the discovery of the neutron. And in fact, this meeting with Landau, Bohr, and Rosenberg in Copenhagen actually took place before Chadwick had discovered the neutron. And the basic idea was that Landau realized, well, if you can collapse further than a white dwarf, whatever the nature of the other body, and he didn't have the neutron when he began thinking about this to draw on, it's going to be something of nuclear densities. And so this idea of, and this photograph, for instance, is from this paper that I'm referencing and shows Bohr and Landau together in Copenhagen. So this idea that there might be some object of nuclear densities much denser than a neutron star, about the size of a city as opposed to the size of a planet, was somehow in the air at this time, because independently in California, Walter Baade and Fritz Zwicky were also hypothesizing. This was after Chadwick's discovery, and they did talk about neutron stars. And this nice cartoon shows Baade at the telescope. Perhaps it's on Mount Wilson, maybe it's the 100-inch Hooker telescope, I don't know. And then Zwicky is taking a nap. It's night, in the middle of the night, obviously, but he says, call me when something explodes up there. I want to check on those figures, because their idea achieved enough notoriety that the Times, the LA Times, was explaining to its readers what a neutron star was and what these supernovas were. And so it's worth noteworthy that for Baade and Zwicky, the key thing about a neutron star was that if you had such a hyperdense object, that meant that gravitational collapse could proceed much further than it otherwise could. If the white dwarf star at the size of a planet was the endpoint, then that's as far as you could fall, and that limited the amount of energy which could be extracted in gravitational collapse. But they knew at this point that supernova, admittedly, probably they were mostly detecting type 1a supernova, but anyway, that supernova were visible in other galaxies, that other galaxies were far away. This was all emerging in this period. And therefore, you needed a really dramatic source of energy to power these objects. The idea of neutron stars then was originated in the 1930s, but it lay dormant in many ways. Even if it had briefly made the newspapers, a great many people, probably including many astronomers, simply forgot about them as an object. But many theorists remembered. And an example of that, that fact that it was still a live idea in the minds of theorists, is given by Freeman Dyson, writing an article which appeared in a book in 1963 called Interstellar Communication. And the idea of the book was to talk about essentially SETI type topics. Could we detect other intelligences? And Dyson was critical of accepted ideas in this field. And he said, well, how do we know what an arbitrarily advanced civilization would be like? He said, for instance, if I guess he was saying, if I was such an arbitrarily advanced civilization and I wanted to travel around the galaxy, what I would do is I would find a couple of neutron stars, and he admits at this stage that their existence of such objects is uncertain, and then I would park them in very close orbit around each other. And then I would use the gravitational slingshot effect to power my starships as they travel through the galaxy at high speeds. And he said, an unintended, I mean, anticipated, but not necessarily the point of the exercise, result of this would be that these aliens would be broadcasting gravitational waves reasonably strongly around the galaxy. So he said, if we want to find them, maybe we should look for them. So here are our little green men. They're inadvertently broadcasting gravitational waves around the galaxy. And Dyson is aware of the work of Joe Weber. Here is Joe Weber, who was the pioneer of gravitational wave detection, who at this time in the early 1960s was developing these bar detectors, such as you see here, to try to see gravitational waves. And Dyson says, presciently, that neutron star binaries should be detectable with Weber's existing equipment at a distance of the order of 100 megaparsecs. And he says it would seem worthwhile to maintain a watch for events of this kind using Weber's equipment or some suitable modification of it. So, of course, considering that neutron stars haven't even been discovered yet as an actual object, it's very prescient that Dyson is anticipating one of the main sources for the gravitational wave detectors of today, at a time when certainly nobody was talking about binary black holes. So this was the beginnings of the development of a theoretical catalog for the field. Now, admittedly, the first element in such a catalog had, of course, been Baden-Zwicky's conception of a supernova, and that had helped guide Weber in his thinking. And these are important, of course, because such ideas may be very useful to people beginning a detection program, because they might at least give you an idea of what frequency band you should be searching in. And although Weber had already made his decisions by the time Dyson was writing, nevertheless, probably the work of Baden-Zwicky and then others who had come after gave him some ideas, because certainly supernova collapse was a major possible source for Weber. Now, to give you an idea of the status of the field at this time, in 1962, the third General Relativity Conference was held near Warsaw in Poland. And Feynman was there, Weber was there, and Feynman, it seems, persuaded Weber to give a seminar on his efforts to detect gravitational waves. And I believe that this is a blackboard upon which Weber, during his talk, actually gave a little diagram of his detector, and you can see the way it's suspended and the detectors in the middle of the aluminum bar. And while he gave this seminar, in the proceedings of the conference, an unidentified questioner, presumably somebody calling out from the back of the room, asked in what one can only imagine is a way intended to raise a laugh, asking Weber, have you measured any Dyson neutron binaries yet? Incidentally, curious fact that this conference took place in 62. The book I mentioned that Dyson published about the neutron binaries was in 63. So I guess I judge from this that he was already talking about it in 62. So at any rate, we can see here that the idea seemed somewhat outlandish. Weber was certainly swimming against the tide in trying to detect these things, when you consider that the kinds of sources that would prove detectable were already were at this stage being viewed as, if not science fictional, at least somewhat risible. These pictures and some of this information comes from an excellent paper by Marek Damianski on this famous conference, which appeared in General Relativity and Gravitation. The reference is there on the right. And another picture from this conference shows Weber there on the left speaking with Dmitry Ivanenko just beside him. And according to Damianski, Ivanenko, having discussed Weber's program with him, went back to Moscow and talked with Vladimir Braginsky at Moscow State University, and that was the germ of their very important effort to detect gravitational waves. And so the idea was already spreading even before Weber had actually succeeded, claimed to have succeeded in detecting gravitational waves, half a decade later. Okay, obviously, I feel I should say something about the actual discovery of pulsars. That's a very well-known story, so I won't go into it in any great length. There's a picture here of Jocelyn Bell. Jocelyn Bell and Tony Hewish were the main people, and Martin Ryle, in the first detection of pulsars. This is Bell with the instrument, the Interplanetary Scintillation Array, which was designed to look for quasars at the Muller Radio Astronomy Observatory in Cambridge. And the aliens are back. The little green men are back because, of course, famously, when they first saw this pulsar, this pulsating star, they thought, well, is this an alien civilization? And then when they discovered more than one, they said, well, they're probably not all aliens, so probably this is a natural phenomenon. So the aliens keep popping up in this early history of neutron stars. And this was a very nice picture showing I guess, artifacts of the detection. Probably the name of the pulsar, CP1919, and the term pulsar may have been added in later here to show you, but here's I guess, an output and showing what the pulsar signal looked like. The term pulsar was invented right away by Hewish, I believe, but I presume that wasn't written down at the time. I'm not sure. But you can see the date here, 1967, and the publication was in 1968. And I have to say at least a word, but again, it's beyond the topic of the paper, that, of course, infamously, Jocelyn Bell was not awarded the Nobel Prize. Martin Ryle and Tony Hewish were. It's blatant that the reason that they didn't give her the prize was that she was a woman. People have argued that it was because she was a graduate student. We'll come back to that topic in just a minute, because there happens to be a very good counter argument to that. And if I sound like I can't help but talk about it, I'll mention that I was born in the same small town in Ireland that Jocelyn Bell was. I've never met her. I was hoping to meet her at a conference this year, but it's been canceled by COVID. So not only is it not that typical for a woman to get a Nobel Prize, but not very common for Irish people to get Nobel Prizes either. So I feel I should object. It has to be said that there's really no excuse for not giving her the Nobel Prize. And although they're long dead, presumably the people who were responsible for that, I hope they were ashamed of it themselves in their own lifetime, but probably not. At any rate, more of a note to our story. We have, how did people recognize that the pulsars were neutron stars and not little green men? And of course, the theorists came right back into it. They had kept this idea in their heads. Probably the main figure associated with pointing out that neutron stars were a good fit to explain pulsars was Tommy Gold, who presumably was, in his own words, delighted to find that he might actually be useful in science. The discovery of quasars, of course, had brought the gravitational physicists to the attention of the astronomers and gave rise to the field of relativistic astrophysics. And in an after-dinner speech at the first Texas Symposium on Relativistic Astrophysics, Gold said, well, everyone is pleased, especially the relativists who are delighted to find that people are actually interested in what they have to say. So here was, a few years later, another example of this. Okay, so obviously pulsars have been discovered, but what about the binary pulsars? It's actually true that the small size of the neutron star permits not only that long, extra long collapse to power a supernova, so the extra energy that you get out of the gravitational collapse. But again, their small size allows them to be in a very close orbit, so you have a much closer binary system that is possible with a non-compact stellar object. And so the result is that you can have a really detectable gravitational wave system from a binary. A binary star system is the perfect way to generate gravitational waves, except that typically they're not going to be close enough. But with neutron stars, that's a possibility. And then in late 1974, Joe Taylor and Russell Hulse, two radio astronomers, searching for new pulsars, came across the first Dyson neutron binary, right? So now one has actually been discovered, the famous PSR 1913 plus 16. And of course, it's worth mentioning that this discovery was made with the Arecibo dish in Puerto Rico. And now this sadly is a fallen giant. This is a picture of the state of it today. This is, of course, very recent. I'm sure many of you have seen news of this sad event. And in fact, just as an example, Arecibo played a pretty big role in the Nanograv consortium of a pulsar timing array, which is to detect gravitational waves using pulsar timing. And that project shows increasing signs of success, but it now looks like they will have to seek other ways to observe a number of their pulsars because Arecibo is no longer available to them. Again, I've spoken of this elsewhere, so I'm only going to give it short shrift right now. But after several years of observation, Taylor and his collaborators were able to show that this system was undergoing orbital decay in agreement with the prediction of Einstein's quadrupole formula. So this was the first evidence that gravitational waves were real. Although, of course, there was considerable theoretical controversy about that. I won't go into it, however, today. Except to note, again, an interesting thing from the point of view of historians of science, during the 1980s, as they continued to make measurements on the decay of the system, discrepancies began to turn up as they got more and more precise, discrepancies with the theory. And then it was pointed out by Thibaut Damour that this could be due to the fact that PSR 1913 and 16 weren't in our inertial frame. They were, of course, it was halfway towards the center of the galaxy, and it was orbiting the center of the galaxy at a different radius and therefore with a different acceleration, centripetal acceleration. So Damour and Taylor were able to use this idea to measure the distance to the center of the galaxy at a time when this was not quite as accurately known as it is now. But Taylor, when I spoke to him, felt that they hadn't really gotten the credit for that because, of course, they didn't quite feel able to assume that the GR prediction from the quadrupole formula was correct at that stage because of the theoretical controversy there. So it shows that interesting tip-over point when you go from testing a theory to assuming it's true and using it as a way to develop further increased knowledge in other ways. And of course, here is the setup. Russell Hulse was a graduate student at the time of the discovery of PSR 1913 plus 16, but he was given the Nobel Prize. So although, as I said, people have argued, oh, well, they didn't give it to Jocelyn Bell just because she was a graduate student, I think it's pretty clear they didn't give it to her because she was a woman. We have a very good case in a very closely related episode. Well, of course, in the 1990s and subsequently, interest in Dyson neutron binaries was strengthened by the routine measurement of gamma ray bursts, because these were considered a candidate binary mergers, right? The two neutron stars have been drawing together in PSR 1913 plus 16 for millions of years. Eventually, they crash into each other. The energy released in that was thought to be a possible explanation for gamma rays. And so that certainly was another factor in helping convince funders to go ahead and build gravitational wave detectors like the two LIGO instruments shown here. And of course, in 2015, and then the announcement in 2016, along came the first detection by LIGO of gravitational waves, and that led, of course, to the 2017 Nobel Prize in Physics. Barry Barish, I think, will be speaking later in the workshop today, one of the 3 Nobel laureates of 2017. But after the first observing run, in the middle of the second observing run, a third gravitational wave detector joined the project, and that was Virgo, shown here. I think I accidentally showed Virgo twice instead of Livingston. My apologies. But at any rate, there's Virgo. So Virgo joined in the summer of 2017. And I do recall talking to people in the LIGO-Virgo collaboration at a LIGO-Virgo collaboration meeting earlier in the year. and hearing, and at least one person said to me that they had worries. Virgo, of course, hadn't joined at that point because it was trying to bring its sensitivity down enough. And so there were worries that its sensitivity wouldn't be good enough to where it would really be helping and making detections. But then, not very long after it joined, pretty quickly, on August 14, 2017, Virgo achieved its first detection. So this was the first time that 3 detectors had seen the same signal, a black hole binary merger called GW170814. And just 3 days later, came another detection, GW170817, which was the first binary neutron star. Up to that time, all of the detections had been black hole binaries. That was detected by the LIGO instruments, but not seen, at least initially in the data, by Virgo. So this was a real stroke of luck, I feel, because I'm not the first person to point this out, but I think it's very interesting to look at the reasons why this would have been important. Virgo had only been involved in the run for a short time. Obviously, there would have been concerns about, whether it was, operating at the sensitivities needed. Had they not had the first detection, the fact that Virgo didn't initially see GW170817 might have been put down to problems with Virgo. But as things were, it was possible to ask, why didn't Virgo see this? And the answer that was proposed is that, well, it was in a part of the sky that was blind to Virgo. There are certain areas of the sky, fairly small, which a gravitational wave detector is blind to. So for instance, if you have 2 arms and the wave comes splitting the difference right down the middle, then the 2 arms will respond the same and you won't see anything. So the fact that Virgo had a different orientation to the 2 LIGO detectors was here key. And it was extraordinarily lucky, first of all, the perfect positioning of this source, and then the fact that they had already had confirmation that Virgo was working properly. And so the upshot was that they were able to pretty confidently say to astronomers, look, you ought to look in just this part of the sky. And you have to remember that with only 2, or even to a considerable, certainly with only 2 detectors up to that point, they would say to astronomers, look in this whole huge area of sky, and that's not very helpful. And so famously, astronomers did see the object in question. So here we have optical imaging of the galaxy in question, and there, indicated with a red arrow, is the actual afterglow from the binary neutron star merger. So this event is known as a kilonova, and so it's important to note it's visible in gravitational waves, gamma rays, and the afterglow is visible even, for instance, by optical telescopes, and it was in fact observed by space-based gamma ray observatories as well. I can't resist having a slide that's punning a little bit, since earlier I had a title that was Tommy Gold and neutron stars. So this time, of course, you may know that these neutron star mergers, these kilonovas, are thought to be a source of much of our gold and other heavy elements. And just to give an idea of the extent of multi-messenger astronomy, this is a map which shows the observatories which have seen these the first binary neutron star merger. So we have 3 gravitational wave observatories in yellow, but a host of other of astronomical observatories and space-based gamma ray detectors and others. So there is some interesting history and sociology of science going on here. Several gravitational wave physicists I spoke to mentioned the culture clash between them and the astronomers, right? So there was a considerable degree of friction. How to assign credit, who gets to be at the press conference, author order on papers, a lot of interesting things there. I won't try to go into all of them. One thing I will mention is one of the astronomers I spoke to who acknowledged these conflicts said in his view it was the funding agency, NSF, that was responsible. He said essentially they're funding the astronomers to be competitive, but they're funding the gravitational wave scientists to be collaborative because they have a whole program that's devoted to LIGO, and you have to be part of the collaboration if you want to get funding under that program. So interestingly, he was very deterministic in terms of analyzing the sociology. So it was quite interesting. Another example, LIGO initially would only accept a detector output if the signal passed a 5 sigma test coming from particle physics, but at least one signal failed this test. But if you're doing astronomy, you'd like to be complete. So does that mean that you have to change your standards? And there are a number of issues that come up. I'll try to just skip lightly over this slide, but I'll mention, for instance, the people who make LIGO work. Right now, they're scientists, but if they become telescope operators, if LIGO Virgo become observatories, that would be a very different social standing within the field of science. So astronomers used to be quite skeptical of LIGO. Many of them, in fact, initially opposed it, and said, look, we could build a lot of telescopes with this, although we've just been reminded that there's a limit in the long run to how much we can expect to see, but still. I do live with an astronomer, and she has a little joke. Well, I once appeared on television, and I was talking about the history of astronomy, so they described me as an astronomer, and for a long time afterwards, she would introduce me to people by saying, he's not really an astronomer, but he does play one on TV. So I'm proud to report that when the first LIGO detection was announced, I got a promotion in our family. After we saw the press conference, she kindly turned to me and said, now you're really an astronomer. And so perhaps the day of gravitational wave astronomy has finally dawned. So thank you very much.
Thank you very much, Dan. This overview on the up to the post-discovery of binary neutron star. Are there any questions? We don't have much time. Unfortunately, I mean, you talked a little bit more than 20 minutes, so we have a couple of minutes. If there are questions, please write in. So there is a comment by Adele.
You don't know the half of it.
There is also a comment by Virginia Trimble, but now we hear Adele, maybe Virginia later. I don't know.
It was just something for the speaker to respond to.
So sorry, I didn't get. Virginia, do you want to?
No, I just said to the speaker, you don't know the half of it.
About Jocelyn?
No, about gravitational waves.
Oh, yes, yes. That's true. I would like to hear the other half of it. So
sometime.
Virginia, definitely we'll have to talk.
Some other time. Yeah.
Yes.
Okay, so Adele, do you have a comment?
Oh, yeah. Thank you so much, Dan, for your very beautiful talk. I was just reminding, Dyson's writing, and I also reminded in that writing that you quoted at the beginning about neutron binaries, he also figured some very futuristic idea of how collecting energy from gravitational waves. So I remember he made this in that some very strange and what the comment I wanted to say is that the same year in which that writing Dyson appeared, there was also the first calculation of gravitational radiation emitted by pointless masses, two pointless masses, so a binary system of point masses, by Peters and Matthews. So it was the same year in which there was also the mathematical calculation of the first for the first time of the radiation emitted. It's just a comment, but thanks so much.
Yes, thank you, Adele. Yes, that is a very interesting aspect of the story, and indeed, work like Peters and Matthews, which was very important in the development of the field. But nevertheless, there was a strong reaction against work of the type of Peters and Matthews by some people in the field who said, well, this can't really be used because, as you say, it's point masses, and we should have extended masses and so on. We should have more rigorous calculations. So that's a very interesting story to see the theorists and the experimenters moving along side by side with different controversies in each field, but then in the end reinforcing each other in a way that makes it particularly interesting history.
Thank you very much. I think that we have to move ahead. It was a very interesting talk. Okay. There is, I think, somebody. Okay. Thanks a lot again.